As we get into significant circuit analysis, we'll need to talk a little bit about circuit elements and the diagrams that go with them. The picture on the left is a sketch of an electric circuit, but it's got too much detail and a lot of irrelevant ones. It doesn't matter where the wires bend, for instance, or that the battery is on the right of the resistor and not on its left. All that matters are the connections and circuit elements themselves. So we tend not to draw pictures of circuits. Instead, we draw circuit diagrams. Abstract cartoons that capture the important relationships. The circuit diagram corresponding to this picture is this. What we have is we have the battery, which we represent with that, and we have the resistor, which is represented with that, and finally our capacitor, which is represented with this. So here's a visual dictionary of the common basic elements. We have, for instance, we have, of course, a battery, which kind of looks like that, at least traditionally, but we represent it as this little thing with extra plates. Again, remember, this is meant to capture the idea of voltaic plates, where you actually had plates of copper and tin, I think, in an acidic bath. And so we had alternating types of metal. By convention, and we should probably say this somewhere, the longer one is the plus type. All right, so the long terminal is the positive terminal. We have a wire, which is drawn in a ridiculously simplified fashion. We have resistors, which are these jagged little lightning bolt things designed to have the idea of the equivalent of a longer path, like a wire that's been crumpled up. We should be careful. We don't mean a thing which is coiled. All right, so do not mistake that for this. We'll come back to that later, not this chapter, but later chapters, to talk about what that might be, but this is jagged, not looped. A bulb, which looks like sort of a little filament inside a circle. And a junction is just where the wire is split. Capacitor with the two plates, what we expect. There is a variant for the capacitor, which is to have one straight and one curved thing, like that. And I'm not really sure why that's used. I think it's just to make sure that you don't confuse it with batteries. But, and sometimes you might have to indicate that it's polarized, in which case we would put the positive is usually here. So that would mean that you have to connect it so a positive charge ends up there, or else bad things happen. That happens with it because of the dielectric that's inside. And a switch, and the purpose of switch, of course, is that when it's open, no current can flow, and when it's closed, it's just a wire. All right, so a switch looks like this. They're always drawn in the open configuration, even if you're going to, of course, throw them at some point. The reason for the purpose of switches, of course, is to make sure current doesn't flow as soon as you finish connecting up the circuit, which could be bad, or even before you finish connecting up the circuit, depending on how you have it. Some conventions. Wires are drawn as line segments that meet at right angles. They are always drawn as vertical and horizontal, though they don't have to be. Higher potentials on batteries are drawn on top whenever possible, on the page, meaning top on the page. And individual elements are labeled with their names, such as R1 for a resistor, and or their numerical value, 10 ohms, written next to them. All right, so let's take this apart. Draw a blue circle around the diagrams that show the same circuit. Let's see if anybody has the same as A. A is a battery in parallel between a capacitor and a resistor. So anything coming out of the battery can go either through the capacitor or through the resistor. So if we look at B, we come out and we can go through the resistor, or we can go through the capacitor. So this one is the same as that one. Let's look at C. C says I come out, hit a resistor, go through no resistance here and back, and then through here and a capacitor and back. So the resistor is not in the parallel branch, so it's not the same as A or B. D, we might come out and either go through the resistor or we go through the capacitor and back, which means D actually turns out to be the same as A and B. As an aside, this is not a crazy circuit at all, because although I think it's going to cut well, you'll get current through the capacitor until it's at equal resistance, equal voltage to the battery, and then just a regular thing here with a charge capacitor. So this could be a circuit that probably is used to charge that capacitor. All right, draw a circuit diagram showing a 9-volt battery connected to 2 branches. One of the branches a 6 microfarad capacitor, and the other branch 2 100 resistors in series. So I'm going to draw my battery and label it. Your textbook likes to squiggle in, I'll do it here once, fill these things in. I think just to say, like, that's the element. I don't think that serves any actual purpose, but they like to do that. All right, we're going to come out and have 2 branches. And one of those branches is going to be a capacitor. And then restore. And we'll say the capacitor they said was 6 microfarads, so I'll do that. And the other is going to be 2 resistors in series, and just to be visually distinct, I'm going to pick a different color for the second resistor, and then go back. Aesthetically, it would be nicer if these connected up. So I'm going to, has nothing to do with the circuit per se, but I think it looks a little nicer. And we know that this guy is 100 ohms, and this guy is 100 ohms. And there's our circuit.